Alright, let's go. Number 10. The Solar Standing Waves. A team of helioseismologists at the Max Planck Institute for Solar System Research was doing something almost administrative, recalibrating rotation measurements using 20 years of data from the Solar Dynamics Observatory's helioseismic and magnetic imager. The goal was routine: refine the numbers. Standard convection models predict that large-scale flows on the Sun should behave like slow, churning currents, drifting westward at speeds tied directly to the Sun's rotation rate. Predictable, boring even, then Bernal-Pteen, Aaron Birch, and Laurent Gazan found something that shouldn't have been there. Persistent wave patterns, tens of thousands of kilometers across, racing around the solar equator in a retrograde direction and moving 3 times faster than convection theory allowed. Published in Nature Astronomy in 2018, the paper didn't offer a mechanism. It offered a measurement. The Sun was doing something its own physics said it couldn't. The failure parade started immediately. Magnetic damping was proposed, the numbers didn't fit. A revised convective coupling model was floated. It explained the direction, but not the speed. Some researchers suggested the waves were relics of formation, frozen patterns from 4.5 billion years ago that never fully dissipated. No one could rule it out. No one could confirm it either. These waves aren't cosmetic. They modulate the buildup of magnetic energy that eventually erupts as solar flares, the same flares that can disable the GPS satellite currently sitting somewhere above your head. A star 290,000 times more massive than Earth is running a background process nobody has decoded, and it's steering the weather of near-Earth space while it does it. What is actually driving a wave that physics says is moving too fast to exist? The equator wasn't the only place keeping secrets. Number 9. The Missing Neutrinos. In 1967, Raymond Davis Jr. lowered a 100,000-gallon tank of cleaning fluid into the Homestake gold mine in South Dakota. He wasn't hunting for a mystery. He was trying to directly confirm nuclear fusion in the Sun's core by counting the neutrinos it should be producing every second. Standard solar models, built on decades of nuclear physics, predicted a precise flux. This was supposed to be confirmation, not confrontation. Davis counted roughly 1/3 of the predicted number. For 3 decades. John Bacall at Princeton reran the solar models repeatedly. The predictions held. The deficit remained. It wasn't resolved until 2001, when Arthur MacDonald's team at the Sudbury Neutrino Observatory in Ontario proved the missing neutrinos weren't missing. They'd changed identity in flight, a process called neutrino oscillation. Published across several Physical Review Letters papers, and eventually awarded the 2015 Nobel Prize in Physics. Before oscillation was confirmed, the failure parade ran long. Detector contamination was blamed first, then ruled out through repeated calibration. A flawed solar model was blamed next, and rejected because every other prediction from that model checked out. Even after oscillation solved the headline number, discrepancies lingered in specific energy bands. The beryllium-7 neutrino line still doesn't match predictions as cleanly as physicists would like. The sunlight warming your skin right now left the Sun's core tens of thousands of years ago, and took 8 more minutes to cross space. It is the product of a process that took physicists 30 years just to count correctly. If the count was wrong for 3 decades, what else about that fusion engine are we still measuring incorrectly? The core wasn't finished being strange. Number 8. The Coronal Rain Anomaly. Solar physicist Patrick Antolin and collaborators were studying something mundane: how coronal loops, the glowing magnetic arches you see in every solar eclipse photo, cool down and lose plasma. It's basic thermodynamic bookkeeping. Standard models treat the cooling plasma as a simple fluid falling back toward the surface under gravity, accelerating the way a dropped stone would. Using high-resolution footage from the Solar Dynamics Observatory's atmospheric imaging assembly, Antolin's team instead documented plasma condensing mid-loop and drizzling downward in clumps that decelerated and clustered in ways simple freefall could not explain. Velocities and structures inconsistent with the magnetic field geometry mapped for those same loops. The rain wasn't falling. It was negotiating. The failure parade followed the usual script. Thermal instability models were adjusted to account for clumping. They explained the clumps but not the deceleration. Magnetic tension was invoked to slow the plasma. The numbers only worked for some events, not others. Turbulent drag from the corona itself was suggested, and remains, at best, a partial fit. It sounds abstract until you remember that coronal rain is a visible symptom of how the sun redistributes the energy that eventually reaches Earth as heat and radiation. Every model used to forecast solar behavior assumes we understand this basic falling and cooling cycle. We don't. Not completely. If scientists can't fully model something as simple as plasma falling under gravity, what does that say about the models predicting the sun's next major outburst? Sometimes the mystery isn't in the plasma, it's in the silence. Number 7. The missing sunspot cycles. In the 1890s, astronomer Edward Walter Maunder wasn't discovering anything new. He was combing through 2 centuries of dusty observational logs, cataloging historical sunspot counts to extend the record backward. An act of archival housekeeping, not a hunt for anomalies. The 11-year sunspot cycle was already well established. Regular, rhythmic, reliable, then Maunder, building on earlier work by German astronomer Gustav Spreer, found a 70-year gap. Between roughly 1645 and 1715, sunspots nearly vanished. Not fewer spots, almost none. Across 7 decades where the cycle should have peaked and troughed 6 or 7 times. The period, now called the Maunder Minimum, coincided with the coldest stretch of the Little Ice Age in Europe. Later researchers, including Elizabeth Nesme-Ribes and Jean-Pierre Ribes in a 1993 Nature paper, attempted to argue the historical count was simply undercounted due to observational limits of the era, a theory that has since been largely discredited by independent evidence from tree ring carbon-14 records confirming genuinely suppressed solar activity, not sloppy note-taking. The dynamo models that generate sunspots in the first place still cannot predict when or why the sun would switch itself off for 7 decades, or what would trigger it to switch back on. Nothing in solar physics forbids this from happening again, starting an unknown number of years from today, for reasons no model can currently anticipate. We assume the sun's rhythm is guaranteed. History says otherwise. The surface wasn't the only place moving on its own schedule. Number 6. The solar G-modes. Eric Fossat and his team weren't hunting for a hidden interior. They were sifting through 16.5 years of data from the Golf instrument aboard the SOHO spacecraft, refining pressure wave measurements used for standard heliosismic calibration. The solar equivalent of tuning an instrument before the real performance. Standard stellar models assume the sun's deep core rotates at roughly the same pace as the surrounding radiative and convective zones. Buried in the noise, Fossat's team detected a faint gravity wave signature, suggesting the core completes a rotation once every week. Nearly 4 times faster than the 27-day rotation observed at the surface. Published in Astronomy and Astrophysics in 2017, the result implied the sun's core has been spinning at a leftover pace since formation, insulated from the braking forces that slowed the outer layers over 4.5 billion years. The failure parade split the field. Some argued the core retained primordial angular momentum. Others, including Kieran Jain and Sylvain Korzenik in later analyses, and Vincent Schunker's 2018 team specifically, disputed the detection method itself, arguing the signal was too faint to be conclusive. As of the most recent published work, no consensus exists. If confirmed, it means the object generating every photon of sunlight you've ever seen has a core spinning independently of everything above it. A body within a body, keeping its own time. Which raises the uncomfortable follow-up, what else is different down there that heliosismology simply cannot see? The interior wasn't done contradicting the surface. Number 5. The unexplained polar vortices. Solar physicists working with NASA's Twin Stereo spacecraft, positioned to give the first ever clear view of the sun's poles. We're mapping polar magnetic structure to improve long-range space weather forecasting, a practical, unglamorous engineering goal. Standard magnetic field models predict a roughly symmetric, gradually shifting polar field, especially compared to the chaotic activity near the equator. Instead, in observations compiled around 2013, researchers documented rotating, vortex-like magnetic structures encircling both poles, appearing and dissolving on a cycle roughly matching the Sun's own 11-year activity period, with no complete model explaining their formation, geometry, or disappearance. Explanations offered so far remain partial at best. Some researchers propose the vortices are magnetic remnants dragged poleward by meridional plasma flow. The timing fits loosely, but the internal rotation speed of the vortices does not match predicted flow rates. Others suggest interaction with the heliospheric current sheet, untestable with current instrumentation. No paper has closed the case. Earth has its own polar vortex, one that governs winter weather across entire continents when it destabilizes. The Sun's polar vortices are larger, more energetic, and almost entirely unexplained, sitting at the source of the solar wind that shapes space weather around our planet. If we can't yet model the vortices at the poles of our own star, how confident should we really be in decade-scale space weather forecasts? Even the Sun's youth has a contradiction baked into it. Number 4. The faint young sun paradox. In 1972, Carl Sagan and George Mullen at Cornell University weren't investigating a crisis. They were establishing a timeline, mapping how stellar brightness increases as a star ages along the main sequence, a foundational exercise in stellar evolution. Standard astrophysical models are unambiguous. A star like the Sun was roughly 30% dimmer 4 billion years ago than it is today. At that brightness, Earth's oceans should have been frozen solid. Geological evidence says otherwise. Zircon crystals and sedimentary rock formations dated to 3.8 and even 4.4 billion years ago show clear signs of liquid water, rivers, sediment, erosion. On a planet that, by stellar physics alone, should have been an ice ball. Published in Science in 1972, the paradox triggered decades of failed patches. An enhanced greenhouse from ammonia was proposed. Ammonia photolyzes too quickly under early UV radiation to survive. Elevated carbon dioxide was proposed next. Geological siderite deposits from that era don't contain nearly enough CO2 to account for the required warming. A more massive, faster-fading early sun was proposed to explain both problems at once. Direct evidence for it remains inconclusive. Every explanation for why you exist on a planet with liquid water instead of ice depends on solving a paradox that has now outlasted the careers of the scientists who first identified it. If the standard model of solar brightness is right, how was early Earth ever warm enough for life to begin at all? The heat problem didn't end in Earth's ancient past. It's happening right now, above the Sun's own surface. Number 3. The Coronal heating mystery. In 1939, astronomer Bengt Edeln and physicist Walter Grotrian weren't chasing a paradox. They were trying to identify strange spectral emission lines observed during solar eclipses, lines so unusual that for decades scientists assumed they belonged to an undiscovered element, tentatively named coronium. It was meant to be a straightforward, if tedious, exercise in spectroscopy. Standard thermodynamics predicts heat should decrease with distance from a source. The visible surface of the Sun sits at roughly 5,500 degrees Celsius. The corona, extending millions of kilometers farther out, should be cooler still. Edelin identified the mystery lines as highly ionized iron. Iron stripped of 13 of its electrons, a state that only exists at temperatures above 1,000,000 degrees. The corona wasn't cooler than the surface. It was 200 times hotter, despite sitting farther from the fusion furnace generating the heat in the first place. Nearly a century of failure parade has followed. Simple thermal conduction was ruled out immediately. It violates basic heat flow. Alpha wave heating, magnetic waves rippling up from the surface, was proposed and partially supported, but can't account for all the observed energy. Eugene Parker's 1988 nanoflare theory, millions of tiny undetectable magnetic reconnection events, remains the leading candidate, and was one of the direct motivations for launching the Parker Solar Probe. As of its most recent close passes, the mechanism still hasn't been definitively confirmed. The layer of the Sun closest to Earth, the one shaping the solar wind that reaches your planet every second, runs on a heating mechanism physicists still cannot fully prove. After 85 years and a spacecraft named specifically to solve it, why does the corona still refuse to explain itself? At least the corona gives a warning before it strikes. Sometimes it doesn't. Number 2. The solar flare precursor silence. Space weather forecasters at NOAA and affiliated institutions weren't looking for a flaw in their methods. They were refining predictive models, trying to identify the magnetic shear and stored energy patterns that reliably precede major solar flares, essential applied work meant to protect satellites and power grids. Standard flare theory predicts detectable buildup, shifting magnetic topology, rising free energy, visible warning signs in magnetogram data before an eruption. Then came flares like the X9.3 event of September 6, 2017, one of the most powerful eruptions of the last decade, which showed no significant precursor signature in the monitoring bands forecasters rely on. The active region looked, by every existing metric, unremarkable, right up until it wasn't. Multiple prediction frameworks, including the long-used Macintosh Sunspot classification system, failed to flag these events in advance. Machine learning models trained on historical precursor data have since been tested against them and, in several published retrospective analyses, missed the same flares their human predecessors did. No unifying trigger mechanism has been identified for flares that erupt without warning. An X-class flare with zero forecast lead time is not an abstract inconvenience. It's the scenario that knocks out GPS, disrupts aviation communications, and threatens the power grid supplying the device you're using right now, with no advance notice at all. If the largest eruptions on the sun's surface can occur without any detectable warning, how would we ever know one was coming? And the biggest anomaly of all wasn't found in a flare. It was found in the wind. Number 1. The Parker probe's unexpected switchbacks. In 2018, Justin Casper at the University of Michigan and Stuart Bale at UC Berkeley led instrument teams on NASA's Parker Solar Probe, launched to fly closer to the sun than any spacecraft in history. Their goal was foundational: measure how the solar wind accelerates as it leaves the corona. Standard models predicted smooth, outward-streaming magnetic field lines, gradually weakening with distance, a clean, well-behaved system. During the very first close solar passes, the probe's instruments recorded something else entirely: sudden, violent S-shaped kinks in the magnetic field, snapping backward toward the sun and then forward again within seconds, later named switchbacks. Reported across 2 papers in Nature in 2019, the switchbacks appeared far more frequently, and with far more energy the closer the probe flew to the sun, directly contradicting the smooth field assumption used in nearly every prior solar wind model. The failure parade is still ongoing. Magnetic reconnection events in the low corona were proposed as the source. Later Parker passes found switchbacks in regions where reconnection shouldn't be occurring. Alphean wave turbulence was proposed next. It explains some switchbacks, but not their clustering into dense, rapid-fire patches. Small magnetic jetlets erupting from the solar surface were proposed most recently, and remain unconfirmed as the sole cause. Every particle of solar wind that eventually reaches Earth's magnetosphere, the shield protecting every satellite and power grid on the planet, carries this unexplained structure with it, a signature scientists still cannot fully trace back to its source. After 6 years of direct measurement from inside the corona itself, why can't we explain the most basic behavior of the wind the sun sends toward us every single day? None of these 10 anomalies live at the fringes of solar physics. They sit inside its most tested, most foundational models, the equations used to build every textbook, every space weather forecast, every assumption about the star keeping you alive. The sun isn't confused about how it works. We are. Each entry on this list is a place where careful, credentialed scientists followed the data exactly where it led, and the data simply stopped cooperating. The universe isn't hiding secrets from us on purpose. We just haven't finished asking the right questions yet. About the one star we've had 93 million miles and 4 centuries to study. If you want to see more videos like this, click the video on screen now.